Okay, welcome to 4.3, Conditional Probabilities. Conditional probabilities are calculated after other information is known or given. This is where you want to find the probability of event A happening after you know that event B has already happened. If you know that B has already happened, then you don't need to consider the rest of the sample space. You only need to consider the outcomes that make up event B. Event B becomes the new sample space. We call this new sample space the restricted sample space. We denote that with an R. Remember, a sample space itself is denoted with a capital S, capital S. If you always write a restricted sample space when doing conditional probability problems and use this as your entire sample space, you will have no trouble with conditional probabilities. The notation for conditional probabilities is the probability of A given B. That's how we read it. How we write it is with a vertical line. So that vertical line between the A and the B is read given. The event following the vertical line is always the event that is known to have happened. In other words, that's the restricted sample space. Now, what this means is we've essentially got information. We've got new information. One way of looking at conditional probability is this. How does this new information cause me to revise my estimate of the likelihood of the other event? And this is our first look at what leads to Bayesian probability, or in fancy terms, Bayesian analysis. Let's look at lots of examples. Let's be really careful about the sample spaces and the restricted sample spaces. Let's look at how knowing something affected something else. So all of this is laid out. I'm going to highlight it as we go through. Suppose you roll 2 dice. What is the probability of getting a sum of 5, given that the first die is a 2? So since you know that the first die is a 2, then this is your restricted sample space. So here is the sample space, all the possible outcomes in which the first die is a 2. R is, no great surprise, 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, and 2, 6. Now among this, those are the only 6 possibilities we have to consider. We know that the first die was a 2. Out of this restricted sample space, the only way to get a sum of 5 is 2, 3. There's one way out of 6. Therefore, the probability that the sum is 5, given that the first die is a 2, is 1/6, not 36th. We're not looking at all the outcomes, only those outcomes where the first die is a 2. That's the denominator. There are 6 of those. And in the numerator, only that one outcome, 2, 3, where the sum is 5. Now let's ask a different question. What's the probability of rolling a sum of 5? Now that's different from the probability of rolling a sum of 5 already knowing that the first die is 2. So let's take a look at where this takes us. So when we consider all 36 possible outcomes, remember we have no given information in this. 4 of them, 1, 4, 2, 3, 3, 2, and 4, 1, had a total of 5. 4 of them, but 4 out of 36. So without any knowledge of the first die, the probability of getting a 5 is 4 out of 36, 1/9, or about 11.1%. But when we knew that the first die was a 2, it changed our probability to 1/6, or approximately 16.7%. In other words, knowing that the first die was a 2 increased the probability that we would roll a sum of 5. So one thing affected the other. Let's look at rolling 2 dice again. What's the probability of getting a sum of 7 given that the first die is a 4? Now before I go through the arithmetic, and I will go through this, I will look at the restricted sample spaces, I will ask both questions. Remember that a sum of 7 is unique. In each column and in each row, you can get a sum of 7. That is, with each possible first roll and with each possible second roll, you can get a sum of 7. So, in other words, it's already distributed throughout the possibilities, throughout the event space. So the first die being a 4, that's just a subset that's completely representative of every other row. So I'm going to claim just from that thought experiment that the knowledge that the first die is a 4 is not going to affect the sum being 7. And you can go back to that table to convince yourself of that. But let's go through and work through this. So since you know that the first die is a 4, this is the restricted sample space. So R is every pair of rolls that starts with a 4. 4, 1, 4, 2, 4, 3, 4, 4, 4, 5, and 4, 6. Out of this restricted sample space, the only way to get a sum of 7 is 4, 3. So the probability that the sum is 7, given that the first die is a 4, is 1/6. Now we have to go through this again and find the probability of rolling a sum of 7. That will tell us whether the probability changed by knowing that the first die was a 4. Now notice that when we're asked to find the probability of rolling a 7, we need to consider all 36 outcomes. So the denominator is 36 again. Of those, 6 of them had a roll of 7, and so we got the probability of 6/36, and 6/36 reduces or simplifies to 1/6. So that means that the two probabilities are the same. So just like we were proposing at the beginning, knowing that the first die is a 4 does not change the probability of getting a sum of 7. So I'm going to say that again. This means that knowing that the first die is a 4 did not change the probability that the sum is a 7. This additional knowledge did not help us in any way. It is as if the information was not given at all. So in the second case, the events that the sum of 7 and the first die of rolls of 4 are called independent events. One does not affect the other. In the first case, the events a sum of 5 and the first die is a 2 are dependent events. Knowing that we had a 2 changed the probability that we could roll a 5. And there's a nice simple way of convincing yourself of that. There's no way to roll a 5 if your first die is a 5 or a 6. Because that 5 has to be added to something and 6 is already too big. So knowing that the first die is a 2, at least there is a potential that you'll get a 3 in the second roll and that'll add to 5. Events A and B are considered independent events if the fact that one event happens does not change the probability of the other event happening. So let's just summarize that. Two events are independent if the probability of one does not change the probability of another. Now let's say that in symbols, exactly that same idea, but now stated in probability notation. If two events are independent, then the probability of A given B, well, B didn't affect A at all. So it's just the probability of A. So I'm going to say that highlighted bit once more. The probability of A given B is the probability of A. And continuing with the two events being independent, the probability of B given A is the same as the probability of B. A does not change the probability of B happening. Neither affects the other. Suppose you roll 2 die. Are the events a sum of 7 and the first die is a 3 independent? So we're going to go through and we're going to compute all of those probabilities. The sum of 7, given that the first die is a 3, so we're only looking at that 3 row, and we see that that happens 1 time out of 6. And then we can, for thoroughness, ask the question, what's the probability that the first die is a 3, given that the sum is 7? Now our restricted sample space is that diagonal where the sum is 7, and we see that the first die is a 3 1/6 of the time. Then we look at the events separately. The probability that the first die is a 3, well, that happens 1/6 of the time. The probability that the sum is a 7, well, that's also 1/6. Therefore, these events are independent. Let me point out something. Any other sum, this doesn't work for. If the sum is 8, if the sum is 5 or 6, this doesn't work. And let's go through and see that. Suppose you roll 2 die. Are the events sum of 6 and the first die of 4 independent? And I'm going to not do this entirely arithmetically the way I did the others. I'm going to instead do this in words. Notice that once you see that the first die is a 4, so you've rolled the first die, it's got a 4. The probability that the sum is 6 has increased. That is, these two events are independent. Now, why has it increased? It's increased because the first die could have shown a 6. And if the first die had shown a 6, there is no way that that second die could add something to it and still be a sum of 6. So basically, by seeing that the first die is not a 6, we've changed the probability. We've made it more likely that the sum can be 6. In other words, for these two events, one affects the other. So they are not independent. Suppose you pick a card from a deck. Are the events Jack and Spade independent? And I'm going to do this the same way. Knowing that you've picked a Spade does not change the probability that the card is a Jack. Similarly, knowing that you have picked a Jack does not change the probability that the card is a Spade. These events are independent. Let's look at a similar one from that same setting of a deck of cards. Suppose you pick a card from a deck. Are the events Heart and Red independent? We could go through and do the arithmetic and find each of the conditional probabilities, or we can say this. Notice that once you know that a card is a heart, it must be red. So if it's a heart, the probability of being red is 100%. However, only half the deck is red, so knowing that the card is a heart changes the probability that the card is red. Similarly, knowing that the card is red changes the probability that it's a heart. Half of the red cards are hearts, but only a quarter of the deck is hearts, so these two events are not independent. Now, this last question is one of those that's meant to put a boundary around an idea. It's meant to say that your intuition serves you, that there's essentially no such thing as gambler's luck. There's no run of things. So it asks the question, suppose you flip a coin 50 times and get a head every single time. What is the probability of getting a head on the next flip? Now, this is a classical statistics course. So what I'm going to put here is what we say in a classical statistics context. There's no such thing as gambler's luck. The probability of getting a head on that 51st flip is 1/2. In other words, it's the previous history of that coin tells us nothing. Now, a quick aside here, because if you look at this and you say that's utter and complete hogwash, something fishy is going on, you have to be clear of the context, but I actually agree with you. If I sat down with someone, never flipped a coin with them before, and they say, hey, look at this coin I've got, and they flip the coin 10 times and get 10 heads in a row, and I'm thinking, well, that's pretty unusual, and then they flip it all the way up to 50, and they've got 50 heads in a row, the Bayesian statistician in me probably is saying what the practical side of your personality is saying, and that is, this coin has 2 heads. So let's be really clear on this. Classical statistics assumes that there really is already a kind of preconceived notion of what could happen and the likelihood of that happening. But Bayesian probability and Bayesian statisticians are open to the idea that something could be completely different, that we could be learning new information here. And in fact, the solution that I proposed, that the coin has 2 heads, may not be true. Maybe there's a magnetic field that the coin is flipping through. Maybe the table is moving so that it catches the coin when it's got the tail below it. There's all sorts of things that could make something like this work. My father was a magician, and I'm sure he could figure out a way to do this. Classical statistics, we say, nope, past history does not affect the future. Bayesian statistics says maybe there's more going on here than I initially considered. One of the odd ways that this statistics is developed at this level is that we've talked about the probability of events A or B, and we've defined that in terms of the probability of A and B. But we haven't actually yet spent a lot of time talking about how to compute the probability of A and B without looking at a table, without looking at the entire sample space. So we're returning to that, and we're asking the question, how can I compute the probability of A and B? Now, glancing at this page, you can see that there's 2 formulas, and they are in fact different. So in the first one, we have a conditional probability, the probability of B given A. And in the second one, we simply have the probability of B. And so you might say to yourself, my goodness, there is some subtlety going on here, and that's based on whether the events are independent or not. So if the two events are independent, then we simply multiply the probabilities together. And one of the links that I have put in with this chapter is a discussion, a video about the woman who was convicted of murdering her 2 children under the assumption that those events are independent. So if you're looking at this and saying, who really cares? It's very easy to get these wrong, and the consequences can be huge, and certainly something that would affect any one of our lives. Now, that's great, and I'm going to say one thing before I talk too much more about this. You'll either like this next comment when I have the 2 probabilities of B given A and probabilities of B highlighted. You'll either say, that sounds great, or you'll say, nope, I'm going to stick with the fact that there are 2 formulas. So while these 2 are highlighted, I'm going to say something. When I'm done saying it, I'm going to delete those 2 highlights. So here it is. I claim that I don't need to write these as 2 separate formulas, that I could always write it as the probability of B given A. And remember why. Because if A and B are independent, the probability of B given A is the probability of B. So this rule is a little bit more specific than it needs to be. It's a little bit less robust than it needs to be. That first rule in the first row with the probability of B given A, that's actually good enough, because remember, it is identically equal to the probability of B when the 2 events are independent. Okay, and as promised, once we ended that conversation, I would delete these 2 and we would treat these 2 as 2 separate equations. So if the 2 events are dependent, if one affects the other, then we need that conditional probability. And in fact, that's exactly what dependent reminds us, is that one affects the other, that one is contingent on the other. Similarly, if they're independent, one doesn't affect the other, and we can simply say multiply those 2 probabilities together. One of the interesting things that we can do with this, and our first look towards the direction of Bayesian probability, is just doing a little algebra. So if I look at that first equation and I see the probability of B given A in that first equation, I see that I could solve for the probability of B given A if only I could get rid of the probability of A. I then notice that the probability of A is attached by multiplication. Multiplication is undone with division. So if I divide both sides by the probability of A, I can get the probability of B given A by itself. So a little algebra there, and from it we've gotten a result that tells us a formula for given probabilities, for conditional probabilities. Now let's very quickly get a very tangible, practical example. I've already given the example of use of statistics in the courtroom and how that can be tremendously misapplied just by misinterpreting independent for dependent events. Let's talk about a standard deck of playing cards. Suppose you pick 3 cards from a deck. What is the probability that they are all queens if the cards are not replaced after they are picked? So this is the second example we've seen of that. So now we're doing a little bit of arithmetic with these situations. So the cards are not replaced. So what that means is that we're looking at 3 separate probabilities. In the first case, there are 4 queens out of a deck of 52. So we say the probability that in the first pick we get one of those 4 queens is 4 52nds. Then we don't replace it. So in the next pick, there are only 51 cards left. And similarly, there's only 3 queens left. So we're multiplying. We're interested in an and statement. That they're all 3 queens means that the first is a queen and the second is a queen and, let's move on to the third is a queen. Remember, we haven't replaced the first or the second queen that we've drawn. We now have both of them. We've pulled 2 cards out of the deck. we've pulled 2 queens out of the deck. For that third pick, there's only 2 queens left, and there's only 50 cards left. So the numerator is decreasing by 1, and the denominator is decreasing by 1. There's lots of ways to do this, but I noticed that each of these factors, each of these fractions simplifies. In other words, there's a 4 in 52. That leaves a 13 behind, so when I simplify that first one, I get 1/13. In the second, I see that 5 plus 1 is 6, so I see that 3 goes into 51. In fact, it goes in 17 times. And the second one, well, there's certainly a 2 in 50. That goes in 25 times. So I simplified this just because I didn't want my calculator to have to do quite so much work. And then I did some multiplication. 1 times 1 times 1 gives me my numerator of 1. And then downstairs I get 5,525, which is an interesting number. When we actually perform that division, we get a relatively small number. Tenths, hundredths, thousands, 10,000ths, 100,000ths, millionths. 181 millionths is the probability that we would pick 3 queens in a row. Now, a very similar question, but illustrating the importance of independent versus dependent events to the way we compute probability. Suppose that we pick 3 cards from a deck, and we're interested again in the probability that they're all queens, that is a queen and a queen and a queen, so that and means the multiplication rule kicks in. But now the cards are replaced after they're picked and before the next card is picked. So replaced after they are picked. So in other words, theoretically, we could pick the same queen 3 times in a row. So let's take a look at this. There are 4 queens out of a total of 52 cards, so the probability of the first pick being a queen is 4/52. But then we replace it. And by that I'm taking it to mean that we shuffle it and we're not trying to do anything suspicious with the likelihood of pulling another queen. And again, there are 4 queens. We just returned the one we pulled. And there are 52 cards, so the second pick is independent of the first. And because we do this again, the third pick is independent of the first and the second. So we're left with 4 times 4 times 4. 52 times 52 times 52 in the denominator. Let's simplify each of those. 4 goes into 52 13 times. So this is really 1/13 times itself 3 times. So 1/13 times 1/13 times 1/13 is 1/13 to the 3rd power. So I did that in my calculator and out popped 1 over 2,197. Notice that's smaller. It's actually smaller by a half in terms of how many ways there are to get that. So this happens more often because we're returning those queens to the deck. 455, tenths, hundreds, thousands, 10,000s, 100,000s, tenths, hundreds, thousands, 10,000s, 100,000s, millions. Yeah, 455 millionths. So relatively small number, but more than twice as likely as when the cards are not replaced. Here's an interesting health issue. Leprosy is an extraordinarily virulent disease. It's an extraordinarily easy to transmit disease. So we're going to look at World Health Organization data by region, so by continent and region, and then also by income group. So high income, upper middle, and lower income. Countries are ranked by the amount of income they have. It's a rough measure of how much access people have to health, clean water, clean air, things of that nature. This is called a two-way table because we can see the data arranged in 2 ways. In other words, we can look only at columns and talk about income. We can look only at rows and talk about region. We've got a total in the bottom right, that's 222,545. Notice that that is the total of the columns and the total of the rows. So we're looking at people based on what region they're in, what the income of the country they live in is. This allows us to ask a lot of probability questions. It allows us to determine whether certain things are independent or dependent. So let's get started. This is another one where I'm going to be jumping back and forth to the table and doing a lot of highlighting. Find the probability that a person with leprosy is from the Americas. So notice it says a person with leprosy. All we know about this person is that they are one of the unfortunate 222,545 people with leprosy. And we want the probability that if you somehow randomly selected people afflicted with leprosy, you'd get someone from the Americas. So we then ask, where is the total for the Americas? Well, if I add up all these numbers, I get the row total, which is 36,817. So among all the leprosy sufferers in the world, 36,817 of them are from the Americas. So we form that fraction and we learn that about 16.5% of people with leprosy are from the Americas. The second question asks, find the probability that a person with leprosy is from a high-income country. So again, this is talking about everyone with leprosy. The denominator will be the same. So now we're finding the column total for high-income countries, and that's 264. So this probability is 264 out of the total 222,545. When you do that arithmetic and round to 4 decimal places, you get about 0.0012. So if we said that correctly, let's see, that is what? Tenths, hundredths, thousandths, 10,000s, 12 10,000s. Find the probability that a person with leprosy is from the Americas and a high-income country. So, of course, key here is the idea of and. Now, if you're like me, you'd probably be thinking, well, this is time to use our formula. One of the nice things about a table is every piece of information's already there. You don't need a formula when you've got a table. You just pick out the information you need. Americas and high income. So we go back up here and we say, where does the high income row and the Americas row and the high income column overlap? They overlap with the 174 folks who have leprosy in a high income country. So why is that not deleting? Okay, so I'm going to highlight that 174, and that is the numerator, people in the Americas and from a high-income country, out of the total. The total hasn't changed. We don't have any given probabilities yet. Find the probability that a person with leprosy is from a high-income country given they are from the Americas. So, of course, that given tells us that we have a restricted domain. So we're only looking at people in the Americas. So in this two-way table, we are only looking at the Americas row. We're given that they are in the Americas. And this is the first time that we've had that restriction. So this is the first time that the denominator will not be 222,545. It will be the total for the Americas, 36,817. Now let's see what else it asks us. A high-income country in the Americas. We're only looking at this one row, and we see that the high income in the Americas is 174. So 174 over 36,817. And when we do that, we can see that the probability of being from a high income country, given that you're from the Americas, is 174 over 36,817. That simplifies to 0.0047. Find the probability that a person with leprosy is from a low-income country. So this is not a given probability. It's just asking that someone randomly selected with leprosy is from a low-income country. So now we're only interested in the total of the low-income countries. Here they are. Let me scroll up so we can see the top of that table. 27,923 is our numerator. The denominator is everyone, and we perform that division round to 4 decimal places. Find the probability that a person with leprosy is from Africa. So we look again at that chart. So we're saying among all the folks afflicted with leprosy, what is the probability that they're from Africa? So we pick out the African total, and we divide that by the total of all folks suffering from leprosy. Find the probability that a person with leprosy is from Africa and a low-income country. So we're now interested in that and again. That means that we're going to go inside the table, Africa and low income. So what is that? 15,928. So 15,928 over the total. Find the probability that a person with leprosy is from Africa given that they're from a low-income country. So we're now doing a conditional probability. We're only looking at the folks who live in low-income countries. So when we go back here, we are only looking at the numbers for folks from low-income countries, namely 27,923, and there's Africa at 15,928. You've got it in front of you. So when we click back, those same two numbers will appear, and there they are. The number of low-income folks from Africa over the total percentage of African sufferers. So what this means is that if you are from a low-income country and have leprosy, 57% of those folks are from Africa. Now let's ask perhaps the more interesting question, and that is whether these events affect each other. So in question number I, we're asked, are the events that a person with leprosy is from Africa and a low-income country independent events? Why or why not? We can scroll back and look at the probabilities of being from Africa and the probability of being from Africa given that you're in a low-income country and see that the probabilities are different. It is affected by the income of the country in Africa. There's a tremendous variety of incomes of countries. There's a lot of countries in Africa with different income levels. And as a result, it's not surprising at all that those are in fact independent. Africa has a tremendous diversity within it. Similarly, in question number J, we're asked, are the events that a person with leprosy is from the Americas and a high-income country independent events? And similarly, we can see that there are, again, a lot of variety within the Americas, and as a result, these are not independent. So the incidence of leprosy in the Americas, just like in Africa, is affected by the income of the country. I'm going to make a separate video for the workbook section of Bayesian probability, and I'm going to post that after this. I'm also going to have a video for the project portion of Bayesian probability, and that'll also be separate when we get there.